Good afternoon, everyone. Thank you for coming to another of our PhD seminars. Today's talk will be held by Philipe Dias. He's a visiting PhD student here, staying for 6 months and coming from Marquette University. And today we'll talk about fine image segmentation. Right now he's working under the supervision of Professor Francesco Done.
Thank you, Elena. So you simplified my introduction. So as she said, I'm from Marquette University. In case you don't know where it is, it's in Milwaukee, a little bit north from Chicago. And what I'm going to talk about today is essentially a summary of what I did during the 3 years of my PhD. And I will use that and the applications I've been working on, which in flower detection and a little bit in activity of daily living analysis, also to provide you a little bit of an overview of the field in image segmentation, things that are out there, which kind of limitations there are, which kind of further developments and contributions we made to improve the state of the art on that. So first I will talk about the applications, why do we care about them, and what are the needs that we have for such applications. I will focus first on the flower segmentation task that we have been trying to do as a way to show you a little bit what are the common approaches for image segmentation, and then we also developed an annotation tool that helps annotating with pixel level accuracy segmentation masks. And then a little bit more at the end, we talk about the project we have been developing together with Professor Francesco Done and also Damiano worked a bit on that, not only a bit, but a lot. And especially in the gay segmentation part, that's one of the last ones that I'm going to talk about, is something that I'm continuing what he developed, but was not able to finish it yet, let's say. So starting with the applications, the first one in flower segmentation, we talk about bloom intensity estimation. That essentially means counting the number of flowers that you have in fruit orchards in the early growing season. So this is important to guide processes like that, which is called thinning. Essentially, you need to get rid of some of the flowers because otherwise you have way too many fruits, let's say apples, growing near to each other. This means they won't reach proper size, shape, and all the characteristics you would want from a good fruit to be sold in the supermarket and so on. And also the fact that if you know how many flowers you have, you can correlate to, or can estimate what's going to be your final yield. And this helps doing all the strategic planning for merchandising, packing, and so on. So this is that's why the USDA, US Department of Agriculture, was interested in that. So we have been collaborating with them in this project. And the way that's currently done, you have someone walking around such environments and try to visually guess how many flowers you have, which is pretty tough. If we take a look at this static frame here, we already have a bad time trying to say how many flowers we have. So our goal at the end, a long-term goal, is to have something like you have a tablet, you snap a picture that goes to the cloud, you have a deep learning algorithm that can then tell you where are the flowers, and in this case, how many are there. And we are also trying to have the best segmentation as possible, because if you can segment them, you can think about automatic process of thinning, that is removing the flowers. And there are also some other research being done, for instance, let's say replacing the bees for doing pollination with sprays, robotic sprays, and so on. And what makes it even harder is that we want it to work for all different possible scenarios, not only for apple flowers as the previous one, but also peach flowers, and if you have a cloudy day and so on. So you need robustness in that sense. And the other applications in the assisted living problem, I think probably most of you have been around and heard about, maybe from Chiara Martini or Damiano talking about this project, where essentially the motivation is we have the population of people over 60 years and so on worldwide is growing at a pretty fast pace. So that means we have costs associated with assessment of their quality of living or frailty levels getting higher and higher. And the way that usually this activity of daily living they are evaluated, it's based on questionnaires by the physician, the clinician, so that can be costly, that sometimes not as effective because someone might lie to you or something like that, or hide something. So the long-term goal of this whole research is to have automatic ways of doing that. For instance, you have an apartment, you have cameras, and you can detect objects of interest like people, a table, a chair, and so on. And in this scenario, for example, if you know that there's a person here, there is a table, you can try to estimate the interaction there and define activities, say, this person is eating. If you correlate with some metadata like the time, you can say eating breakfast and so on. I'm going to elaborate more on that later. But essentially, if I summarize what I'm talking about, the both applications, the needs that you have is that you need accurate segmentation, fine segmentation if you want to characterize like interaction, like contact and so on. You need robustness to different types of views and illumination conditions. And apart from these two applications, segmentation is also important, for instance, for self-driving cars, where you need to avoid obstacles, or robotics, where you need to do grasping of some kind of object and so on. So there are plenty of applications of this kind of image segmentation problem. So I'm going to start to talk about how we have been, what are the strategies that have been explored for image segmentation using our flower segmentation problem as a case study, let's say. And the first thing is, if you think about all the previous approaches, we can, the most obvious thing would be, let's search for specific colors, which, as we can see here already in this example, won't work well. If you have the same kind of species, the same kind of image, you already have variations, say, in the RGB levels. This is also going to happen whatever the color space you're using. And this gets even worse if you go to another species like the peach flower here that is completely different color characteristics. So you would have all the previous approaches with only color only work under specific scenarios. This is where the idea of the convolutional neural networks and deep learning, they show up. Essentially because they are capable of characterizing complex structures. In a nutshell, I think most of you know what the idea of the basic network, a perceptron, that you can learn weights that are based on errors and like supervised learning that we call. So you have examples of what is the object you're searching for, what is not. You start to adapt your weights for that. And when we talk about the convolutional ones, is that we have structures like filters, let's say 5 by 5. Each of those there is a weight that you're going to be learning the same way that you have on a neural network. And then you're going to be evaluating regions of your image. For instance, you start evaluating small regions, 5 by 5 pixels, you could say. And by doing the training, you first learn, your network learns how to characterize low-level features like edges or something like that. And then with this kind of cascading architecture where you start to have convolutions over the previous bank of filters that you learned in the earlier layers. So the earlier layers learn to identify very low-level features, and you start to aggregate them in more complex ones. And this is what essentially the intuition of why these networks work well for complex classification tasks and image understanding, because they can characterize this kind of complex structures that you would have a pretty bad time trying to hand engineer that. These are called the hierarchical features. So they first were shown to work well in tasks like the ImageNet dataset, which was image classification. You could say that this is already a pretty hard task, but it's the easiest one, so to say, in the image understanding field, in the sense that you just want to say what you have in the image, you don't care where it is. But things start to get more complicated as you want to localize where things are. I want to say, there is a cat and it's there. Or there are multiple categories and they are in these specific places. And the hardest one is if you actually want to have this classification at pixel level. I don't want a bounding box. I want to say exactly what are the pixels composing each of my categories. And if we like the difference between just semantic segmentation, which is saying the category itself, you can also have instance segmentation where I want to differentiate the two cats here, for example. So in this, going from the classification networks that work pretty well, trying to adapt them for segmentation or object detection with bounding boxes. The first idea was, okay, so we have something, a structure like a classification network that does a pretty good job at telling me what I have or don't have in a certain image. So if I want to find where in the image this structure is, the first thing that I can try to think of, I split my image into smaller parts, meaningful parts, and try to say this part has the object I'm searching for or not. So one of the ways you can do that is using a concept that we use here called superpixels, which is essentially clustering together pixels that are nearby each other and share similar colors. So you can have different types of algorithm trying to optimize different types of energy functions. One of the most famous ones, and that works pretty well, is called the sleek superpixels, where the idea is very, very similar to the concept of k-means. You have a 5D space of the x and y coordinates, and then the 3 coordinates of your whatever color space you're using. And then you optimize to form clusters that minimize those distances within each cluster. So this is how you can get then the so-called superpixels. With superpixels in hand, you can define portraits around them and evaluate each of these portraits with a classification network to say, in our case, if I have a flower or not. So this is the basic, the first idea of how to use convolutional neural networks for object localization and detection, and also segmentation. Such that at the end, once you already have portraits, you have the regions you want to evaluate, you train a network specifically to tell me, in this case, I do have a flower, not have a flower. I won't enter in details how we trained this one because I will show you a second version of our flower detection segmentation network works better, and then I elaborate more and fine-tune the procedures and so on. But essentially the idea is we annotated a bunch of images, all the superpixels, then saying there's a flower here, there's not a flower here, train it, and have a network that can characterize your inputs, map your inputs in a feature space when you can easily separate what is a flower from all other types of structures. So whatever you classify, you use then in such a feature space, it's already going to do a pretty good job because it's already fairly separated. So here is just projection of the 3 dimensions of this feature space that our network maps the inputs on. But the problem is naturally that you rely on the quality of the proposals that you're generating. So if your superpixels are bad, like what you would have here in this scenario or in this scenario, you both have not have a flower here, so you're gonna have like an average score in between, and just the classification can't do anything to separate this. So this was the first problem, the basic problem of using this kind of architecture to do segmentation, that you rely on the region proposals. So if our problem is the region proposal, you can think of 2 things. So there are essentially 2 approaches out there, which is either we generate better region proposals or we don't use region proposals at all. So the first approach of having better region proposals, there is, let's say, a family of network architectures called the RCNNs. It's mostly from the Facebook group of research. That the first one, the RCNN and the fast RCNN, is essentially the idea that I show you generating with some sort of external algorithm, like unsupervised algorithm clusters or something that use region proposals and evaluating them. And then afterwards, what they did with the faster RCNN is called, is that they have a convolutional backbone, a convolutional network that extracts features from the network. And on top of these features, you have another network that learns to generate region proposals. So generate region proposals means like bounding boxes here in these cases of different shapes and so on. So these are candidate regions that might have an object according to this network. And then you're gonna get the features that you have in the specific regions and have some, let's say, subnetworks that learn the classification of these object candidates and what is the exact coordinates of the bounding box inside this region proposal. So this is what was this faster SNN. And then for segmentation, what they did is let's put another branch that will learn to segment this object that I found inside my region candidate. So this is one example of kind of results that they can get. It has pros and cons. One pro is that it naturally helps and makes it easier for instance segmentation because you're already evaluating specific regions. So if you have multiple people here, you have bounding boxes that fit each of them. But you can have thousands of these bounding boxes, so you need some good strategy of no maximum suppression, or otherwise you can detect twice or 3 times the same person. And if you have a lot of objects, your computational time is going to be a little bit proportional to how many objects you have, because you have to evaluate each of them. So I can't tell if this kind of approach is better than the other one that I'm going to show you. I've been working more on the other one that is essentially no region proposal at all. And it's something that I also searched for recently, and there isn't much discussion what is better or not. It's an open question. People have been exploring these 2 directions. And the second direction here is essentially the same way that I had originally one output for an image, the classification, the label for the image, I can try to have the classification for a pixel specifically. So we evaluate the image as a whole, but instead of having as an output fully connected layers that will give you the likelihood only if the class itself for the image, we generate like a map saying, this pixel has the probability of 0.8 of being of a person or a bicycle, as in this example. But the problem is you should simply replace your fully connected layers by convolutional layers. What happens is that you have pretty coarse masks at the end. And this is an interesting fact because it helps you to understand how the networks work, and this is how they evaluate the different levels of context in the image. So, as I said, the main characteristic that allows convolutional networks to do well in image understanding is that they learn the hierarchical features because they evaluate different levels of context. So they start evaluating very small regions in the earlier layers, like for example, this small window here. And then in the next layers, they start to evaluate larger and larger regions. If you want to evaluate larger regions, you have 2 options. The most intuitive one you're going to think about, okay, let's make this window larger. But this window here means, say for example, I had 5 by 5 windows, I had 25 weights to learn. If I make like a 9 by 9, I already need to learn 81 weights. That means it exponentially scales up the amount of parameters I need to learn. That means I need more data. And these are already very hungry, thirsty for data. So you don't want to increase the amount of parameters to be learned because it's going to be unfeasible the amount of data you need. So the other alternative, okay, let's keep the windows the same size, but then we make the image smaller. So this is essentially what happens when you start to build these networks with so-called pooling in regions, that you start to downsample your image as you go within the network. So this is fine if you're doing just image classification because you don't care what the things are. So if it shows up my feature that describes what is a person and I can get a score, say, hey, I have a person in the image, fine. But then if I want to do localization, segmentation of where the things exactly are, what you have at the end of the network is a very coarse image of your original input. So even if we try to actually trace boundaries here, we're going to have a coarse mask. So in a very high level, this is why this kind of architecture alone is a problem for image segmentation. So there have been plenty of directions being explored to improve the quality of the mask that you have at the end. So one thing that people have been exploring, okay, let's have like say a mirror network that tries to learn a complex way of upsampling the representation that I have in the middle of the network. So recovering the best way that I can the information that I lost. So there is this kind of there's another one that you start to have some indices coming from the encoding part to the decode part of the network, but essentially both of these types of networks, they are trying to recover the best they can the information they lost. So what you can do then as well is try to not losing as much information. So let's make the windows larger, but instead of increasing the amount of parameters to learn, I can put holes in these filters, which are essentially padding them with zeros, so I can evaluate larger context levels without increasing the number of parameters that you need to learn. So this is what I think the most famous network that does like this is called DeepLab. There's DeepLab 1, 2, 3, and so on. And works pretty well. It's the one that we are using like backbone for our applications. But one thing of keep in mind here is then that you start to have some pretty large convolutional maps within our network. So that means memory scales up pretty quickly in this case. So if you have high resolution images, you might have your not enough memory even with the best GPU around. Still, like as I mentioned, there is two approaches that they try to improve the quality of segmentation. It does improve, but it's still not perfect. So another thing that people explore is doing post-processing on the outputs of those networks. For instance, this would be an output of one of these networks with the dilated convolutions. One of the most common post-processing algorithms that is used to refine those outputs is called, it's a model of fully connected conditional random fields, where you can see here that it's significantly better, the output. But without entering too much details on the formulation and so on of these random fields, it is widely used, it is fast because they model instead of, if you just think of fully connected conditional random fields, you have, say, a fairly high resolution image, you have thousands of edges, you can model that. So they approximate this as Gaussian kernels. But to approximate these Gaussian kernels, you have some hyperparameters that the problem that these hyperparameters cause is that they need to be tuned by means of grid search or something like that for every specific data set you use or every specific network that you use. And this can be quite of annoying depending on your application if you need robustness to different scenarios. So this was the motivation that we had to try to come up with an algorithm that allows you to do refinement but does not have this sensitivity to hyperparameters. We call this a region-growing refinement algorithm, which we developed inspired in the idea of the superpixels. So the basic idea is you have available the image, of course, and the output for whatever network that gives you a coarse segmentation, like this. So in this square map here, whatever is in dark blue is a very low value of prediction, let's call it 0. What you have in dark red is your 1 in the normalized scale. So very high value of prediction, in this case for the airplane category. So if we try to simply threshold this map, we're gonna have a coarse boundary. However, that doesn't mean that that the map is completely useless. As a matter of fact, we know with pretty high confidence that the region here in very low values, they are high confidence background, we call. And in the same way, what is here is a very high value, is a high confidence foreground. Our problem relies in this region here illustrated in red, where we have some intermediate levels. So the first thing that we do in this algorithm, we separate into these 3 areas. And then we combine this region here of high confidence background and high confidence foreground. Here we combine in this region in light gray. That is our high confidence region. And we need to classify the region here of uncertainty based on what we have available for the high confidence region. So the idea is we sample seeds from the high confidence region. So each color here, we have 3 different types of colors. Each color illustrates a set of seeds that we are sampling randomly from this region. And we grow them based on the same criteria that we had for the superpixel there, which is the distance, the Euclidean distance, in this 5D space of your X and Y coordinates in the image, and also your coordinates in terms of color space. So spatial and color similarities. We do this growing based on whatever is the pair, the seed that I have to a neighbor that has this very small distance, we already assign the neighbor to the same category and start to propagate in this way. But the problem is that if we propagate first, just for one set of seeds, you might have this kind of cases where you have what we call a high confidence false positive. So the network does a mistake and it's pretty sure about its mistake. So this mistake would propagate and cause some errors in our segmentation. And that's where comes into place our Monte Carlo strategy with multiple iterations that we sample different sets of seeds, as the ones illustrated in different colors, grow for each of them. Then what's going to happen is that you tend to have the small false positives, they will show up once or twice, but then if you average over multiple iterations, you can get rid of them. So you can recover some pretty good masks from coarse inputs. This is the basic idea of the algorithm. I'm not trying here to convince any reviewer or something, so I won't spend too much time on the metrics. What I can tell you is that we can recover some pretty nice boundary details as from this is what we have from the network. This is what we can recover for this image. In terms of a little bit of metrics, very shortly, is that if you have the conditional random fields heavily optimized for the network itself, let's say deep lab and the dataset itself performs a little bit better than ours. But the fact is that if we keep the same parameterization, bring to another scenario, like another network called FCS on the Davis dataset, which is another dataset for image segmentation, our improvement over the base input from the network in terms of accuracy is pretty consistent, while the CRF is going to drop if you don't have this hyperparameter optimization. So we were pretty happy with the results, and then this became a base for other applications we have been working on. So naturally, the next step would be like, okay, let's use this, combine with some network, and do our flower segmentation. The detail that's missing here is that we need to. There was no data set out there for flower segmentation. So that means we need to collect images, which we got from our collaborators or partners at USDA. What that means we, aka me, had to annotate those images at very high precision at pixel level. So this is where showed up our idea of having a annotation tool for helping with that. So these were the data sets we annotated. As I mentioned, we want at the long term something that is robust in terms of acquisition conditions and also species. So we have here two data sets of apple flowers, one data set of peach flowers, and another one of pear flowers. Different, some of them are doing sunny days, some of them were overcast weather, different types of resolution, cameras, and so on. And this was the one example of the quality of annotation we were able to collect to compose this data set. And how did we do that? So, as I mentioned, the first try that we had was with superpixels, that first approach. So I annotated the image at superpixel level, just selecting which superpixels had flower or not. That already took like weeks of work. So there's no way I could simply select all pixels individually of flowers for images of very high resolution. So what is normally done, has been normally done for compiling such segmentation data sets is that they approximate your objects as polygons. But then what problem is that you have the trade-off. You either need a lot of vertices to have a good boundary of the object, or you're going to do it quick and you're going to have this kind of lousy job. And then if you try to evaluate something that you need very high quality segmentation, this is not very useful. So if I try to use this kind of approach for flowers, I'm going to have to select thousands of vertices, going to have a bad time. So our idea was to, let's use our fresh refinement algorithm to do that as well. In the sense that what the refinement algorithm needs to grow masks is, I need inputs, examples of what is pixels within my foreground, or flowers in this case, and what is not. So we traced some traces here. In blue are parts within flowers. In red, examples of what is hard negative, so to say. So at first we did this with a tablet, just annotated, brought it to MATLAB, extracted the math for each of the categories and grew with the algorithm. And then we could work over pretty nice segmentations. But it was a little bit of this pipeline of not having everything connected. So okay, let's make actually an interface for that. So the idea is then that we made this interface publicly available. It was published in the WACV this year. We did some experiments to show that it's pretty compare a little bit faster what is out there for basically compared to, for example, this interface using polygons. And the nice thing is that because the algorithm is supervised, I don't need to learn it for specific categories or anything. So I can just have like an index and a color here for visualization for each of the categories I want to annotate. I do the traces here and I grow. Perfect. In terms of quickly how the interface is structured, it isn't the most beautiful interface ever because it was my first experiment, my first experience, so it's the first experience of the student who worked with me on like HTML, JavaScript, and so on. But the choices that we made and worked pretty well is we have the user interface itself based on done with HTML and JavaScript. And then we have the whole image processing part, our algorithm and displaying and so on in a Python library that we made a module with that. To connect both parts, we use the Django framework, which is also open source and allows you to kind of forget about all the intricacies of how you access files and exchange files and so on. So simplified out there our task and works pretty well. So very quickly, this is how it looks like. You have the image, you have the options of tracing different types of either what we call the pencil that allows you to draw something quickly without so much precision, like for thicker regions. For some more complex structures or more squared or something like that, you can do trace lines. You just select the extremity points of these lines. You can erase and improve then if you made some kind of mistake instead of drawing everything again. And another thing is that it's intuitive in the sense that if you have something a mask that does not look as you want, it's just a matter of doing more traces or doing it thicker because that means you have more pixels to grow from, so you are in this way improving the quality of your output mask. So it isn't complex to learn how to use the tool. So this is here are some examples from the experiments we did and reported in our paper there. If you have good contrast between colors, it's pretty quick. You just do a few traces. You can do it for as many categories you want. And even if you have then more complex scenarios, like say a bicycle here, you have to spend more time, but we show that you can still get good quality masks. It's just a matter of providing more inputs. So using this interface, then we were able to finally have on hand already a type of architecture we could use, available data set, so we could finally do our flower detection. And essentially our final pipeline, then it looks like this. We are using one of these deep lab networks, which use the dilated convolutions, which work well, but scale up quickly in memory. So for our high resolution images, we had to split then the image into smaller parts and evaluate each of them individually with a network that we fine-tuned for that. And then the way that what the network is going to give you is likelihood for the foreground, that is flowers, and background. This is a little bit weird. It's something that we haven't understood completely why this happens. But the thing is that we use it as a starting point, network trained for like 100-something categories, a multi-class network, which included categories like as trees, flowers, and so on, but with not so much fine output in between the categories, so we need to further train this network. But the idea of using a pre-trained network is essentially that you know that this network is capable of extracting features that characterize complex things, so we can use this network as starting point and just train its later layers to combine the lower level features into features that characterize what is a flower or not. So you don't need to learn a new network to characterize what is an edge or something like that. You just need to make a better use of these features you have available from the earlier layers for your specific task. So that means you have a fine-tuning procedure where you freeze the earlier layers. You have a low learning policy so that your gradient vanishes as it goes deeper and deeper in the network. You just want to change the later layers that are more the higher level features to characterize what a flower is. And then what I was saying is that is weird is that because it was when you have a multi-class network, your scores at the end they will go through a softmax procedure normally, where the scores across all the different classes they are normalized with respect to each other. So you have scores from 0 to 1. If you just get a single branch from that without this normalization, it is unbounded. And then if you try to train that with just like as a binary classification as we try to do, it diverges. We tried multiple things like trying to normalize with respect to the mean and things like that. We couldn't reach anything that would work. So that's why we thought about, okay, let's have two branches then, one learn the foreground, another one learns the background, and they normalize each other at the end. And then, of course, if we just use it, the outputs of both would have something coarse, so we just plug our refinement method to get the flowers at the end. Another detail is that if you take a look at the statistics of the data sets, we have like 5% of the image areas with flowers and all the rest without flowers. So if you just train straightforward, the network learns to detect anything, and you have 95% of accuracy. So we did augmentation with simply mirroring with respect to both vertically and horizontally. That quadruply, you have 4 times the amount of positive examples you had originally, and that already allows you to train your network properly. So once again, without talking too much about metrics, here we have in blue what is correctly detected. We have in red what is missing from the detection, what should be detected was not. And in pink, things that were detected but aren't actually flowers. So in a nutshell, we can detect pretty well. We were very happy with the results for both the test part of the data set we trained on, which is this one, and also the other data sets that it was not seen during training, like this other one, where you have some mistakes that are normally small leaves that the sun is directly illuminated and so they shine and look a little bit like a flower. So this is one failure case we need to handle. And the other failure case is just a matter of examples because it's like the flowers that have not fully opened yet. We didn't have this in the training part, so these buds are something that if we include them in the training set, then we would be able to detect. But the nice thing is that it worked pretty well, even considering it was trained only this data set, works in another data set with another species, another type of illumination condition. Finally, reaching the activity of daily living analysis that I promised. So, as I mentioned, this is a project here, a collaboration with the University of Genoa that has been going on the acquisition of images for a while already. And essentially the images we work on is from this discharge facility where you have cameras that have a view from the common area or from the kitchen. So this is a view from the kitchen, here's from the common area. And especially the common area view brings some challenges for image segmentation, image understanding, that you have a wide angle camera at the top, having a view that you have distortions as you go farther from the camera. So for instance, if you run this image to a conventional network out there, you won't detect this guy that looks like he's floating around. And if you run this part into a network trained for multiple categories, what you can get is like a detection of a refrigerator or something. Because this is what the networks have been trained for, only this kind of nice view. So, first thing we did, because I was here as well in the summer of 2017, was simply we evaluate in a sliding window fashion or multi-stream, if you prefer to call, smaller parts of the image with and without rotation, get the outputs we have and combine, stitch them together afterwards. That already helps to detect these scenarios where we have more complexity. Of course, this is not what we want to have at the end, as we want to model better where to look at, how to stitch things together, but that already gives you some pretty nice results. As you can see for this example here and also for the other video, in red here, chair or sofa, or the blue, the people, in yellow, the table. what we want to do next is to have more temporal smoothing. We're just evaluating frame by frame, so of course there are things that jump around that if you have the most basic probability model, you can already have more smoother. But as a proof of concept, we saw that we can actually use those traditional architectures and refinement module to detect the things we are interested in the image. But the thing is that it's not sufficient to only detect the things that you have in the image, but to see if they're actually interacting. And that brings other aspects that have to be handled. One of them is gaze estimation, which is what Damiano worked recently at the end of his PhD. And to exemplify why is this important, so these are images from a data set called gaze follow. Is one of the few data sets out there specifically for gaze estimation. And the thing is that you might have, for instance, a person, and you might have a computer or whatever in your desk, and the person is not actually interacting with it. So if I just conclude something based on the presence of them, I might be concluding something wrong. So I want to know, have the gaze estimation as a cue of what is the person interacting with. The gaze follow is a data set with quite a few images, I believe like around 10,000 or something, annotation of where the person is looking at. And they also provide a model that is based essentially in two paths, two streams. The first one is you're evaluating the image to say what seems to be the most salient part in the image that would be a higher likelihood that the person would be looking at. And the other one is focusing more around the head of the person, given the eye or the head position, and based on the features that you have from the head, estimate the direction that the person is looking. Then they have element-wise product and some classification strategy to finally predict where is the person looking at. But the problem is that then if we say decide to use this model, we start to have plenty of models for specific things. So we would need a model for file segmentation, another model for the gaze estimation, and then another thing that is important for activity of daily living analysis, something that Matteo is working on, like a pose or gate estimation. So you start to have plenty of things that you combine together, and that would increase complexity of your final model for the application. So this is where Damiano, Francesca, I don't know who else might be involved, and the idea that we could, for instance, use OpenPose for gaze estimation. And OpenPose is a network, a model that provides you, this is one example that I have, pretty nice. It provides you the key points of each specific instance of a person in the image. So you have the positions of joints like an elbow, shoulder, the hands, the nose. They also have some alternative models for like the fingers of the hand, and also the toes and so on. And in a nutshell, the way that they have this model is that they have a detector, like estimating where the position of these key points, these joints, and also they use what is called part affinity fields. This is essentially learning the association between adjacent joints. So for instance, from the direction that you would have the likelihood from your left shoulder to your left elbow. And based on that, there are some bipartite graphs and stuff that they actually do to identify the optimal configuration of joints. They can recover where are the joints, and you have also available these affinity maps. So this is these are the two inputs that we can use to help us in our task case estimation. So I'm calling this year Damiano's net because we don't have any better net so far. Essentially that you have the image, you run through OpenPose, you get the poses that you have estimated, and then the idea is that you get the facial key points specifically, and you have some sort of not so deep network. I think there are two hidden layers there. Train it to estimate the direction of the gazes as illustrated from this red arrows here. So comparing with the gaze follow method, for instance, this is similar to what this pathway would be doing. They use as well the saliency pathway to explore better image features that you have. Especially because sometimes you might have, say, a view from the back, that the OpenPose will not detect the facial key points, like the nose and the ears. So these inputs are going to be missing. So if you want to have an estimation, we need some sort of image feature telling us where the gaze direction might have been. And there is a concept that we are working on with first, which is on saliency detection or pixel objectness detection, which is essentially detecting the things that are foreground or more salient in the image. And the fact is that when you talk about that, it's not only sufficient to use like a variable segmentation or class identifier network, because you can have a very wide range of categories. So at first we are playing then with these models that detect pixel objectness itself, because it works for any kind of category. But then the thing is, if you just get your image run through this kind of pixel objectness network, the person itself that you want to evaluate the gaze from, it will also be salient. So what you need to do, you need to get rid of the person here in this saliency map to go from the image perspective of what is salient to the perspective of the person itself of what is salient. As I said, we don't want to plug more things together, so what we've been playing with, this is what I'm currently working on, is to use the outputs of the OpenPose, as for instance the key parts and also the heat maps that you have available from part affinity fields, to estimate where the person is in the image. So I plug in here the refinement method to improve this output from the pixel objectness network, and most importantly, to grow the inputs that I have from the OpenPose in terms of the heat maps, to actually recover to have an estimate of what is the person in the image, so that I can suppress it from this pixel objectness map, and then I can see what is salient apart from the person that I want to estimate the gaze from. So this is the latest thing that we've been working on. We need to now learn how to combine this saliency detection here from the pre-estimation of gaze that we have based on the facial key features. And yeah, so this is just one part of our future work. Another part of our future work is that, unrelated, is that we are trying to model better now mathematically our refinement module to have more, to improve also its performance, because then you can have like a closed form where you can see what are the gaps in the model. For both projects, for instance, the flower one, we are now able of segmenting the flowers, but we want to count them or maybe remove some of them, so we need to separate individual instances of flowers, so that goes to the direction of instance segmentation. So this is another step we are planning to explore now. And also for the gaze estimation and the activity of daily living, you need as well to separate each individual person in the scene. So instance segmentation is the next step for both projects. So this is what I wanted to talk about. Hopefully you guys were able to learn something. And yeah, so if you have any questions, please, I'm more than happy to answer or try to.
Are there any questions?
I have some questions. In the first part of your talk regarding the counting the flowers or something like that, what do you provide as output? An interval so that you can also give sort of imprecision in your count, or just a number?
So currently what we have is just the segmentation, like this map. The next step that we want to go is then in the direction of counting them based on this. So the first thing that we could think of is just like, we have an average area of the flowers, and from that we have the average area in pixels. We could tell how many flowers you have with a certain uncertainty. But what we actually plan to do is to have the fact that we have videos, so we can have multiple views, so to say. You can track them and try to differentiate specific flowers, the instances alone, and from that provide a counting estimate. So to answer, we don't have yet the counting estimate. When we try to correlate first to give an idea, it's just based on the average area of flowers, but these are what we have in mind to try to do.
The other question, I guess you already mentioned it. So you expect to have multiple views of the same tree, and
Yes.
therefore there is a problem of how to combine the
Yes,
information.
we like in our lab in the Marquette University, I also have colleagues that work more in the temporal and tracking aspect. So our plan is to combine things together because then you have multiple frames. It's the videos that we have available from these data sets, they are very smooth, very good frame rate. So our same tree shows up in 2, 3 subsequent frames. And in this way, you can try to track then the images and differentiate when you have like clusters of flowers to actually in one view they might show up more separate.
Other questions? No? Let's thank you again, Felipe.